Thank you, Joe. Hello, everyone, and thank you again for joining us for this month's webinar series. Today, we will be covering some of the advanced 2.5 axis machining methods. We'll be covering machining of stepped pockets, which is pocket with multiple levels. We'll also talk about machining of islands within pockets. We'll look at machining of open pockets, machining of slots, hole pocketing and finishing up holes using hole profiling, and finally chamfering. And we'll cover this both in RhinoCam as well as our flagship standalone visual CAD/CAM products. So first, I will switch over to RhinoCam and we'll go through a demonstration of programming a prismatic part in RhinoCam, and then I'll follow that up with visual CAD/CAM. So what I have here is a part, a prismatic part that's loaded into Rhino. And as you can tell by looking at the part, we have several different types of prismatic features. We have stepped pockets, as you can see right here in the center of the part, and also has an island in the step pocket. We have open pocket. We have a slot feature in here, holes in the inside the pocket area, as well as on the four sides of the part. So we'll try to cover each of these. Now, as you can see by looking at the part, I already have established a stock in the machining browser. The stock has been defined. The work zero has already been defined, and we've programmed a facing operation. So you can refer to our previous webinar to learn more about how to establish work zero and programming of facing operation that was covered in our previous webinar. So I'm just going to go ahead and simulate this operation in here by going to the Simulate tab and selecting the Play button to run a cut material simulation. Now that we have programmed the facing operation, the first thing I'm going to focus on is programming the pocket, the stepped pocket. So to program a step pocket, we'll go to the 2-axis under Machining Methods, and then pick Pocketing. So once I select Pocketing, the Pocketing Operation dialog shows up. And then in the Pocketing Operation dialog under Part Regions, we will choose Select Curve Edge Regions. And when working with a solid surface geometry, I could directly select face edges or surface edges from the solid model. So in this particular case, I would like to pick the surface edges or the face edges on the top edge of the pocket. So I can either select each face edge individually or chain them together using the chain command in Rhino. Using from the Select tab, you will find Select Chain as one of the options in the Select tab. So I'm going to use Select Chain, and then I'll just pick one of these edges, and it automatically selects all edges that are tangent to one another. So select chain, and then picking on an edge automatically chains the edges in here. And once the edges are selected, I would right click or press enter to accept my selections. Now again, I'm going to repeat the chain command again. Since I have a island within the step pocket, I'm going to pick this as well, and then right click to accept the chain, right click again to basically accept all of the selections of the face edge region, and this will display the machining browser window, the operation dialog back in the machining browser window. Now once we have these selected, we'll go to the next tab, advance to the next tab, which would be the tool. We'll pick a tool for the pocket operation. So in this particular step, I will be selecting a 1/2 inch flattened mill. The feed speeds are set to be automatically loaded from the tool. If you'd like to override these or set a different set of parameters, you could always do that under the Feeds and Speeds tab in the pocket operation. For clearance control for the clearance plane, I'm going to leave this as automatic. The clearance plane will automatically be determined based on the stock and the part. And automatic will clear the maximum height of the part of the stock by 1/4 of an inch. The next step is to specify our cutting parameters. We'll go to the Cut Parameters tab. And in the global parameters, as pocketing is considered like a roughing operation, you'll see that the tolerance is set to 10 thousandths and it leaves a stock of 25 thou. So stock of 25 thou will basically leave 25 thousandths off of the side walls of the pocket, so you could go back and program a finishing operation using a profile to remove the material that's being left along the side walls. Specify the tolerance, stock to leave. You have the option to also turn on cutter compensation if needed. We'll now specify our cutting parameters. There's different types of cut patterns that are available. We'll choose the offset cut pattern. We'll set our cut direction in here. I'll leave it as mixed. And then I'm going to go ahead and leave the step over at the default value of 25% of the tool diameter. The next thing I'm going to do is advance to the cut levels tab in here, where I will be able to specify the total cut depth. So the geometry, what I selected for the pocket boundary is at the top of the pocket. So I'm going to leave the location of cut geometry as at top, since the pocket boundary as well as the island boundary, what I selected, is at the top. The next step is to specify the total depth. I could either enter in the total depth or I can use the pick controls in here, and I can pick 2 points, one at the top edge of the pocket, the other one could be at the floor of the pocket. So the total distance or the height between the top and the bottom is determined. I've used the object snaps in here, so I could easily snap to the edges, the end points or the edges of the part. And once you have the total depth established, you can split this up into multiple levels as needed. And then you can specify your entry and exit parameters. You can apply these at each cut level. And finally, I'm going to select Generate to generate the toolpath. So you'll now notice that the pocketing toolpath has been generated. I can select Toolpath Visibility to display the toolpath. And let's take a look at the toolpath display in levels. So we currently have 3 levels. The first Z level, you can see that it basically creates a pocket toolpath around the entire pocket boundary. On the next Z level, you'll notice that it automatically avoids the island from being machined. So the region heights are automatically taken into account and honored in pocketing operation. You will notice that the island is at a much lower height than the pocket boundary here, as you take a look at it from either from a side view, or if you take a look at from like a front view here. Let me switch to the view here. So you can see that the island region is at a much lower level than the pocket boundary. So the pocketing operation automatically knows the region heights based on how you selected those regions. And as you go through these cut levels here, you can see that it automatically excludes the island from being machined. So in the first level, it clears all the material out. And in the next 2 levels, it automatically accounts for the island. So the region heights are automatically honored in the pocketing operation. Now I'm going to go ahead and run a simulation in here. We'll switch to the Simulate tab and then click Play to run the cut material simulation. I'll hide the toolpath visibility while it's simulating. So we have the pocket toolpath with the island, and there's a few things I would like to point out here. One is there's a finish pass that hasn't been added around the island region in here. So we're going to go ahead and add that in the pocketing operation. We'll double click and edit the pocketing operation. To finish around the island, we'll select Cleanup Pass. So this will add an additional pass to clean up around the island, and it will still honor the stock that's been specified to leave. So since we have a 25,000 stock specified to leave, it's still going to leave 25,000 around the side walls of the pocket and the island areas. So I'm going to simulate it again. So select play under the simulate tab. And now you'll notice that it still honored the stock and it did a cleanup pass around the island region. Now you'll also notice that there is some additional material being left on top of the island. So we would like to go ahead and clear this material, not having to do an additional operation just to clear the island, the material on top of the island. Now to program this in the pocket operation, we will go to the cut levels tab and we'll select this option that's called clear island tops. So this will automatically add an extra Z-level toolpath to finish off the island top. And again, I'm going to basically just split this into two levels. So the first level would finish off the island top, and the next level will basically cut around the island. So I'm going to pick generate. And now let's display the toolpath. And you'll notice that the first cut level is right at the top where the island is. And the next cut level honors both the pocket boundary and the island. So you can see that in just one operation, you're able to program the pocket with the island region.
One quick comment on this, Uday. I just wanted to point out that when you specify clear island tops and you specify a step over, we would adjust the step overs actually to, in a way that you're actually clearing the island tops. So your step over that you get in the toolpath might not be exactly the same as what you specified. It will definitely be below or smaller than the step down value that you specified. I'm sorry, I should have said step down, not step over. It's definitely smaller than the step down value, but it won't be exactly the same. So we adjust that automatically. I hope that's clear. Thanks, Uday.
Thank you, Joe. Going back to the example, so the depth per cut, the step down was set to 0.2. As Joe pointed out, the step down will be adjusted automatically. As you can see in the cut level display, it's automatically adjusted to here. In this case, it's 0.2167. Point to be noted here is the Z0 is at the top of the stock, not the top of the part. So there's a 50,000 height difference between the Z origin of the top of the stock and the part. So that's the reason. And then also the adjusted, so you can see that the step downs are automatically being adjusted here. I'm just showing you the toolpath display in levels. So now that we have programmed the first level in the stepped pocket here, as you can see it, we want to go ahead and program the second level in the stepped pocket. And you can see there's two pockets, one with an island and one with a through hole. So we're going to program the second level, which would be the step pocket here. So to do this, we're going to repeat the same pocket operation. So rather than having to go up to the menu and select a new pocket operation, I'm going to do a copy paste. So I can select the operation, do a Control C for copy, Control V to paste it, or you can use a right click option to do a copy, right click, paste. So we are making a copy of the same pocket operation. Now I would like to edit the operation. So double click on the folder to edit, or right click and choose edit. We would like to now make changes. So I'm going to remove all to drop the current selections, and then I'll pick the pocket boundaries for the step pocket here. So we'll select curve edge regions. And again, I'm going to use the select chain option in Rhino to make my selections much faster. Click on select chain. The continuity is set to tangency. I'm just going to pick, in this particular case, I'll pick on the floor of the pocket. So I'm picking the pocket floor. The edges are on the pocket floor. I'll repeat the same, select chain, pick the floor around the island. Repeat it again for one last time and pick the pocket boundary around the floor of the pocket, the second pocket. So you can see that I'm selecting multiple pockets, one with an island, one without an island. So I can program multiple pockets in one operation, so you don't have to create multiple different operations to program it. So we've selected these 3 pocket boundaries in here, one with an island and 2 pocket boundaries. I'm still going to use the same cutter, 1/2 inch end mill. I'll skip through the feeds and speeds and clearance, as I would like to use the same parameters as the previous operation, and the cut parameters as well. I'm going to skip through that. As you can see, I've left a stock of 25 thousandths again for the step pocket. In the cut levels, I'm going to make a couple of changes, couple of edits. One, the geometry what I've selected here is at the pocket floor. As you can see here, it's at the bottom. So I'll choose location of cut geometry as at bottom. Now, since there are no island tops that needs to be cleared out in the step pocket, I'm going to clear this checkbox for clear island tops, and then we'll select generate. So the toolpath is now generated. I'm going to display the toolpath visibility, and again we have this step pocket being machined in 2 levels. You can see the first 2 levels apply to the pocket with the island, and the next 2 levels applies to the pocket with the through hole on it. So we now program these pockets. Let's go ahead and run a simulation. Select play from the simulate tab to run a cut material simulation. So we now successfully programmed the 2 pockets, the step pocket and the pocket with the island. I still have left 25,000 stock. As you can see here, the stock is being left. We'll talk about how to clear that out using a profiling operation once we program a few other features on this particular model. So now that we have programmed the step pockets and pocket with islands, the next feature I would like to program here is an open pocket that we have, which looks like a notch here on the other end of the part. I'm just rotating the view just to make it easier to analyze it. Now, to program open pockets, we can use 2-axis and facing. So we'll go up to the 2-axis methods and select facing. Now, for the part regions, we will just select the edges on the open, edges around the open pocket, excluding the edge, the bottom edge here. So I can use select curve edge region. I'm going to pick these edges that forms the open pocket. So if you accidentally pick the wrong edge, you can hold the control key to drop it. So I've selected these edges in here, which forms the open pocket. Right click or press enter to accept your selections. Now for the tool, now since the radius on this particular feature is 1/4 inch, I'll pick a 1/4 inch end mill. Set the feeds and speeds and clearance like how you did on the other 2 operations. Under the roughing tab, we're going to specify tolerance and stock. So if you like to finish it to the edge of the open pocket, you can set the stock to 0. Choose your cut pattern. We'll pick the island offset cut pattern. Step over distance, we'll leave it as 25%. In the cut levels, I'm going to specify the total depth. We'll just pick the depth, pick a point near the top edge and the floor. And for the location of cut geometry, I'm going to leave it as at top, since I chose the edges on the open pocket at the top of the feature. Now I'm going to pick generate here. And once the toolpath is generated, when I display the toolpath, you will notice that the tool is entering from the edge where it's open. So, and also it automatically knows the boundaries of the open pocket, so the cutter completely stays inside of the edges that you've chosen here. So to program an open pocket, you can select these edges around the open pocket and use 2-axis and facing, and this will automatically plunge and program your approach and engage entry and exit motions on the open side and the side that's open.
There was a question on why we use facing instead of pocketing for this sort of open pockets. And I just wanted to explain that open pockets, we use facing because facing understands that the tool can approach the material to machine from the sides. That is, there's stock on the outside, so it's open and the tool can actually approach the material to machine from the side rather than plunging in directly. While a pocket or pocketing operation assumes that the material is enclosed on all sides, there's no access to the material to be cut from the sides. So that's the main difference between facing and pocketing. So that's why Uday is used facing here. If you have anything else to add, Uday, please go ahead.
Thank you. So if it was a pocket operation, then you would have had a ramp inside the pocket, so it would be more like treated like a closed pocket when you have a it only works with closed regions. So facing, as Joe pointed out, the cutter enters from the outside or where it's open to basically able to clear the material out. So in this particular case, we programmed it using 2-axis and facing. Now I'm going to go ahead and run a simulation here. We'll select play. Let me slow it down again and then rerun the simulation. As you can see, the cutter starts from the outside where it's open and then clears the material out. Okay, so we just programmed our open pockets in here. In the next step, we have a slot on the end of the part. We would like to program the slot. As you can see, the slot also, it's not just a straight slot, it also has a radius to it here. So you can program open and closed slots using 2-axis slotting. So selecting slotting. Now the slotting operation is available starting with standard and higher configurations. So standard, expert, professional, and premium includes slotting operation. So in the slotting operation for the part regions, I'm going to click on select curve edge regions. Now you'll notice that this particular slot also has a chamfered edge on the top. Now I could select in this case, I'm going to select where the floor or the bottom of the slot as for my part regions. I'm going to use a select chain again. We'll just pick one of these edges and automatically selects all of the edges that are tangent to one another. So the entire slot is selected. I'm going to press right click or press enter to accept my selections. Now I measured the slot. The slot is 3/8 inch in diameter. The width of the slot or the radius at the corner is 3/8. I can go to analyze and measure it again. Analyze distance. I'll measure these 2 points. And as you can see, it says the distance, the width of the slot is 3/8 of an inch. So for the tool, I can choose a tool that matches the slot width. So I'll pick the end mill, which is 3/8 inch in diameter. Feeds and speeds, I'm going to leave it as a load from tool. Clearance is set to automatic. Now let's take a look at our slot parameters. By default, the tolerance is set to 1,000. Stock is set to leave is 0, so which means it's going to finish it right to the edges of the sides of the slot boundaries. The slot direction, you can set to natural or reverse. Cut direction can be climb or conventional. And then in the cut levels, we can choose the location of cut geometry. As we selected the slot region at the floor of the slot, I'm going to choose at bottom. And then we'll pick the depth, the total cut depth. I'm going to pick the top edge and then the floor. So that's about 1/4 inch. I'll split this up into 2 levels. And the cut traversal, I could do zig or zigzag. So selecting zig will return to the same start location for each of the cut levels. And you can control the entry and exit for slotting, very similar to how you can set it in pocket operation. You can ramp into the slot. So selecting generate creates the slotting operation toolpath. And as you can see here, when the width of the slot matches the tool diameter, you're going to get a single line, center line pass on the slotting operation. So let's go ahead and simulate it and take a look at this tool path. So we'll switch to the Simulate tab and select Play. You'll see that it's just creating a single line, a single center line path automatically identified at the midpoint on the center line of the slot. So this is when the slot width and the tool diameter are exactly the same. Now, let's take a look at what would happen when you have a tool that's smaller in diameter than the width of the slot. So I'm going to switch this from a 3/8 inch end mill to a 1/4 inch. So I'll go to the Tools tab in the Objects browser, and I can drag and drop the 1/4 inch end mill on top of the slot operations. So you'll notice that the operation is now flagged, and we've swapped out the tool. So we need to regenerate the tool path to clear the flag. The operation is flagged dirty, which means the tool path needs to be regenerated due to the changes we made. So right click regenerate, and you'll notice that now the tool path for slotting is generated as a trocardial tool path. So based on the tool diameter, what the tool that you select and the slot width, the slotting operation automatically determines the tool path for it. Now, you also have the option to introduce a cleanup pass. So it'll add a cleanup pass once a trocardial toolpath has been generated. So let's go ahead and run a simulation here. I'm going to click play on the Simulate tab. That's the first cut level. That's the finish pass and the next cut level. Now, if your tool diameter is larger than the width of the slot, it's going to warn you, letting you know that it's going to gouge the part. So it's not going to allow you to generate a tool path if the tool diameter is you pick is larger than the slot width. Okay, so we just programmed our slotting operation. The next operation I would like to program is we'll focus on these holes in here. So we have holes of different sizes. We have a larger hole, through hole here, and then we have a few drill holes on the side. So to program these holes, I'm going to, I could program these using pocket operation. However, for holes with tight clearances and precision, we have methods called hole pocketing and hole profiling. So I'm going to use hole pocketing in here and demonstrate how to use it. So under the 2-axis methods, you'll find hole pocketing. Again, this method is available starting with standard and higher configurations of our mill module. Now for the part region, which is the hole feature, you could select a face edge, or you can pick a circle, an arc, or even a point to specify the region for hole pocketing. So I've chosen the face edges from the hole. The next step is to specify a tool. So I'll go with the 1/2 inch end mill. Feeds and speeds, we'll do load from tool. Clearance, set it to automatic. And we'll focus on our cutting parameters in the hole pocketing operation. Now again, the location of cut geometry, it could be set to at top, at bottom, or pick top. So in this particular case, we chose the face edge for the part region at the top of the hole, so I'm going to leave it as at top. Now for the hole depth, I can measure it by just selecting 2 points. By snapping it to 2 points, I can either use near or end point snap. We have the hole depth specified. Now by default, for arcs, use arc diameter is selected. This means the diameter of the hole is determined automatically based on the edge, the curve, or the face edge that you select. Now if you'd like to make the hole slightly smaller or larger, you can override this by clearing this checkbox, and you can input your own diameter for the hole. So if the hole needs to be oversized or undersized, you can override it without having to go back and make changes to the actual drawing or the design of the part. If you leave this box checked, then the diameter of the arc or the hole that you selected is automatically taken into account. The next set of parameters are specifying your cut direction. The hole pocketing is made up of three different types of interpolations. We have the helical interpolations, we have the circular interpolation, and then finally a cleanup pass. So over here, we are controlling the step down distance for the two finished passes in here that we're going to be creating. So this can be set to a distance or a number of levels. If you just like to create a helical path all the way down to the finished depth, and then introduce the spiral motion to go from the helix diameter to the diameter of the hole, and add a finish pass, you can set the step down distance number of levels to 1, add a cleanup pass at each Z level. You can control the step over for your spiral cut pattern. I'll put it as 10%. And for the helical motions, you can control that or set that parameters under the entry and exit tab, where you can specify a helix diameter. You can specify the helix pitch. I'll specify this as 50 thousandths. And then you can choose to create full 360 helixes and apply or output each helix individually. This is where, for controllers which can handle helical interpolations, you can output each helix as a separate line of a GO2 or a GO3 motion. So a circular, so basically you have a helical interpolation with an X, Y, Z, and an IJ. For each of the helix, it'll be outputting as a separate line of code. And then you have your spiral path where it gets from the helix diameter to the hole diameter, and then you have a cleanup pass at the bottom of the hole. So hole pocketing is broken up into three different types of toolpath cut patterns. You have a helical, spiral, and then a cleanup pass. Now the settings to output them as linear or helical interpolation can be specified under machining preferences, under arc output settings. You can control these right in here. Right click, regenerate before you post-process the toolpath for those changes to take into effect. Now, if I'd like to introduce more than one level, I can go back, edit the parameters, and set the number of levels to 2, and then regenerate it. So you'll now notice that there's 2 levels. So start with a helical entry move, and then creates a spiral cut pattern to go from the helix diameter to the edge of the hole, and then a cleanup pass at each level. So this is a great way to pocket holes when you have holes with tight clearances. Now the next operation we'll program here is programming of these 4 through holes. Now you could be doing this with drilling. As I do not have a tool that matches the diameter of these holes, I'm going to measure the diameter in here. These are 0.299, 300,000, about 300,000 diameter. I'm going to be programming this using a hole profiling with a 3/16" cutter. So we'll go to 2-axis and we'll select hole profiling. Now, hole profiling assumes that the hole is either roughed out or you already have cleared out the material, and hole profiling is basically, it follows around the profiles around the inside of the hole, considering that the material inside is already cleared out. Now, if you're going to be using a tool that's just slightly smaller than the diameter of the hole, then you don't have to program like a pocket or a pre-drill operation. You can go directly and program a hole profiling operation. So in this particular case, I'm going to select these edges on the part, on the hole feature as my part region. So I can select these face edges. Right click or press enter to accept it. Specify a tool. So I'm going to go with the 3/16" end mill. Set my feed speeds. Set the clearance. And then we'll go over to the cutting parameters. Now, this operation is very similar to what you notice in hole pocketing, where you can specify your hole depth. You can also control the diameter of the hole. So automatically, it's going to use the diameter of the arc or the curve that you selected to establish the diameter. If you'd like to override it to make the hole either oversized or undersized, you can clear the checkbox and input the diameter. So I'm going to leave it as, for arcs, use arc diameter. We'll specify the helix pitch, very similar to how we programmed this in the whole pocket operation. And again, we have the control to output full 360 helixes and not output partial helixes, and output each helix individually. This is only applies during post-processing, the output each helix individually. And helical interpolations can be programmed in hole pocketing, hole profiling, and also thread milling operations. So what you're noticing here is creates a constant helical motion here all the way down to the bottom of the hole, and it automatically inserts a finish pass to clear it out. So it'll have a constant helical engaged motion here. Rather than programming this as just a 2-axis profiling, you could program it using hole profiling. And again, this can be output as helical interpolation in your posted code. So we program these 4 holes using hole profiling. And you can control or change the helix pitch under the cut parameters, which can be either specified as a height or as an angle. Now, before I program the chamfer operation, I'm going to go back and finish the pocket as we left 25,000 stock around the side walls of the pocket. I'm going to use a 2-axis and a profiling operation. So we'll select profiling, and I'll program all of those in just one operation by using select curve edge regions, and I'll pick the edges on each of the pocket floor. I'll use a select chain option again to automatically chain the edges. I'm going to repeat this 4 times for each of the pocket boundaries and the island. So as you can see now, I've selected all 4 regions. For the tool, I'll switch to a 1/4 inch end mill. In the cut parameters, I'm going to use climb cutting, and for the cutting side, I'll choose determine using 3D model. So the profiling operation will automatically determine which side to place the cutter, either the inside or the outside. So we have the pocket boundary we need to cut on the inside and the outside of the island. So it automatically determines when you have a solid or a surface model right on the edge where you have the in a region where you have an extrusion or a pocket boundary. So the system will automatically determine which side to place the cutter, so you don't have to choose outside or inside. So I'll choose determine using 3D model. Now for the cut levels, I'm just going to say at bottom, since I chose the bottom on each of these pocket boundaries. And then with leaving all the other parameters at the current values default settings, I'll pick generate. And you'll now notice that a profile finish operation is generated to clear up the material in just one pass, in one step. So I'm going to go ahead and hit play to run a cut material simulation. So it clears out that 25,000 stock that's being left from the pocket operations.
So there was a question about cutter comp. If you can show where to set the cutter comp.
Sure.
Good. Thanks.
Thank you. So the cutter compensation can be specified in the cut parameters tab under compensation. You could either set it to auto on or control on. So selecting cutter compensation to auto on or control on will still compensate for your tool for what you program. In addition to that, it'll output a G41 or a 42, depending on whether you're doing a comp left or a comp right in your posted code. So to compensate for additional tool wear on your machine or the controller. So you got to make sure that you're setting the cut direction to either climb or conventional. So you can't turn on cutter comp with mixed cut direction. You also need to make sure your entry and exit has to be specified to lines and arcs for entry and exit. And most machines or controllers would prefer you do a linear as opposed to radial, for the cutter comp to work on the machine. So you can set this to linear. You can specify an angle for it, and then generate it. So now, once you have this cutter comp specified, in the posted code, when you post-process your toolpath, it will show the cut comp in the output. So I'm going to do a post quickly here, and then I'll select a post. And once the code is posted, you will notice a cut comp in the output here. You can see G41 turns your cut compensation on, and then it turns it off on the exit motion. So again, repeats it for each of the profiles. Turns on the cut comp and turns it off. I hope I answered the question. Now, the next operation we're going to be covering here is chamfering. So we will program chamfers. We have a chamfer that's actually built into the feature on the part right here, as you can see it. So let's take a look at how to program this. We'll go to 2-axis machining, and we'll pick chamfering. And again, for the features, now if you have the chamfer that's already modeled into your solid part, or if it's already built into your design, then you would want to make sure that you pick the chamfer edge where the chamfer ends. So I'm going to use the select chain command again in Rhino, and just basically pick this edge so it automatically chains. So we are selecting the edge where the chamfer ends, not where it begins. I'm picking the edge where it ends right in here. So right click or press enter to accept your selections. Now for this, we'll pick a V-mill or a chamfer mill. I have a 45-degree chamfer. So I'll pick the tool that matches the chamfer angle. In the cutting parameters, now the geometry, we're going to say at bottom. So you want to make sure if the chamfer is built into the design, you want to pick the bottom edge and you set it in the cut parameters as at bottom. You specify your chamfer width, and based on the tool that you've chosen, in this case it's a 45 degrees, so the width and the height would be equal. So the height is automatically computed. You can either specify a height or you can specify the width for the chamfer. Now, to keep the tooltip off of the finished edge, you can specify a tooltip clearance. So I'm going to be putting in a 10 thou tooltip clearance. We'll specify the cutting direction. You could choose the side. I could choose inside or outside. And then you can also control or specify your entry and exit parameters if you'd like to apply entry and exit, and then pick generate. So specifying a tooltip clearance automatically compensates for it, so the tooltip is not on the edge of this chamfer. It's being offset both in the Z, and also it compensates for it in the X and Y. So we'll go ahead and run a simulation. So as you notice here, the cut material simulation did not show up on the chamfer operation because the previous operation, I regenerated it, but I forgot to simulate it. So the in-process stock was not created from the previous step. So since I skipped simulating the profile operation after turning on the cut compensation, when I simulated the chamfer, I couldn't see the in-process stock. So I need to make sure that I simulate the profiling, or at least I can do a pause simulate to end. So when I do that, it clears the flag on the in-process stock. So now when I go back and run the simulation for the chamfer operation, you can see the cut material simulation. So please make sure that you simulate all operations prior to the one that you're simulating to be able to view the in-process stock during your simulation. Okay, so we just programmed the chamfer here. Now, let's consider that you'd like to go back and chamfer the edge on the inside of the step pocket. You will notice that this particular edge, it's just a straight edge. There's no chamfer that's modeled into the design. So let's see how we can program it. So I'm going to make a copy of this chamfer operation. We'll do a copy and a paste. I'm going to double click to edit that, remove all, select curve edge region, use select chain, and just pick the chain, right click to accept the chain, right click to accept the selection of the part regions. You can see that the entire region is now selected. We'll pick the same tool. Now in the cut parameters, I'm going to have to choose geometry at top. So when there is no chamfer that's modeled into your part, you want to pick the top edge and you set it at top, and then specify either the width or the height, your tooltip clearance, and then generate. So you could program chamfer operations with parts by just selecting a sketch or an edge where you do not have the chamfer even built into your design. So this is a very nice way of programming your chamfer toolpaths. So you don't really have to model it in your solid model. If you do, you pick the bottom edge. If you do not, you can pick the top edge and you can still program it. Now the last operation I'm going to program to finish completing programming this part would be a profiling operation to profile around the edge of the part. So I'm going to make a copy of one of these operations here. Right click copy, right click paste. And on profiling this part, now as you notice in this particular part, I have an open pocket. So I don't have a continuous chain of regions around the part silhouette. So what I'm going to be doing here is rather than picking the regions on the top edge, I'm going to use the regions on the bottom edge of the part. I'm going to pick the 4 face edges are on the bottom of the part for the profile finishing operation. I'll use a 1/2 inch end mill. In the cutting parameters, I'm going to leave it at determine using 3D model. In the cut levels, I've set it to at bottom. I can specify this total depth, and I can break it up into multiple depths per cut. Generate creates our profile toolpath. We'll select play to run the cut material simulation. So we've now completely programmed this part. We'll take a look at the estimated time for machining based on the parameters that we put in here. You can generate a shop documentation to create your setup information sheet. You can choose one of these templates in here. And finally, post-process this out to your machine tool. Now I'm going to try to quickly program the same using our flagship standalone product, Visual CAD/CAM, exactly what we did, just to recap or summarize how we can program this exact same part in Visual CAD/CAM. I'll try to go through that.
Okay, since we're almost running out of time, I would suggest there were some questions on the drilling, the 4 holes, and using a mill bit for the drilling operations. Maybe if you can show the drilling operations, and then how to use a mill bit and how to linearize the motions, that might be useful.
Absolutely.
And then also there was a question on how to use 3D model for determining depths. So if you can talk about that, I think, and then we can talk about Visual CAD/CAM in another session.
Sure.
Thank you.
We'll do that. Thank you. All right. So to drill these, we can use 2 axes for hole machining and drilling. We can select hole features. I'm going to use select drill points or circles. So I can just basically pick the face edges. Select those face edges from the model. For the tool, we can pick a tool. The drill operation allows you to pick pretty much any tool type. You can either select a flattened mill, or if you want to define as a drill tool with the tip angle, which is like not a pointed tip, which is in this case, you can see the tip angle is 120 degrees. If you put the tip angle as 180, this would basically be like a flattened mill. You could define it as a drill tool, but with a tip angle 180, or you can choose a flattened mill. If you already have one in your library here, I can say I want to go with a 3/16 flattened mill. I can pick that as my tool for drilling, and then set the feeds and speeds, set your clearance, your cutting parameters. Now to drill this hole, you can either program this as a standard drill, where you're going to drill to the depth in 1 pass, or you could program this as either a deep drill or a break chip, where you can basically do a peck and retract, and you can specify your step increment. So I can specify a step increment of 1/8 of an inch, and I'll change it to deep drill. My total depth is going to be 1 inch in here, and then we'll pick generate. So this is basically going to create a a peck and a retract motion. So when I run a simulation, you'll notice that it creates those peck and retract motions. Let me go back and slow it down again. So that creates peck and retract motions. Now to linearize the output for drilling in post-processing and not outputting as a CAN cycle, you'd want to go into your preferences on your machining browser, which is located on the top right corner. You go down to machining, and then under drill cycle output, you select the checkbox, always output as linear motions. So this is going to linearize the output. So when you post-process your toolpath, you'll linearize the output in here using G0 and G1 motions, as opposed to outputting as a CAN cycle, which could be G81 or G82, G83. So that's how you'd go about linearizing the drill output. I hope that answered your question. Now, to going to the next question about how we can determine depth using 3D model. So we can go to a pocket operation or a profile operation. We can select face edges as machining regions. I'm going to pick this pocket boundary right here. I go to my tool. We'll pick a tool for it. In the cut levels, you have use 3D model to detect depth. So when you select this checkbox, the depth is automatically determined based off the 3D model. So when you generate the toolpath, you will notice that the depth will be determined, and you can just specify a depth per cut. If I put in a large value, a depth value that's larger than depth, it'll just insert one level at the floor where the depth is automatically determined, one cut level, and you can see the Z level right there. Or if you specify a smaller value for depth per cut, let's say I put in 100,000s, you'll create multiple Z levels, and the final depth will be where the floor is. So the depth is automatically determined based off the 3D model. And this can be specified under the cut levels tab. Now this can be done in pocketing, profiling, most 2.5 axis operations.